And one of the challenges for this talk is there's such a wide variety of options that makes it really tough to talk in generalities, simply because you've got soil types ranging from clay all the way to pure sand. We've got field shapes ranging from 400 or 500 acres in one open field to 5 acres in one open field. And then that changes the economics immensely. So we're going to try and kind of skirt around the edges of it. Any numbers you see in here, you need to run for your own scenario, because every single one of you is going to have a different scenario. So I'm going to give you an overview of how to do it, and then you can kind of run your own later. So first thing we need to look for is whether your soils are conducive for irrigation. There's a couple of things. Number one, do you need to? There are people that get some outstanding yields, dry land, that may not need to irrigate at all. There's other factors that come into play as to whether the soil will actually take irrigation. It will infiltrate at the rate that we would be applying, because a lot of times we're putting a lot of water on it. Application rate's pretty high. If you get some tight soils, you get some silt loams, or some silty clay loams rather, sometimes that infiltration rate is so low that we end up with problems with making them work. Is there significant upside yield potential? So are you going to gain much by putting irrigation on this field yield-wise? What are going to be your capacities? So in other words, do we have access to enough water? And do we have a shape of a field that we can put a system in to make it economically viable? And then, this is a big one, and it's often overlooked. Do you have the time and patience to really manage this system? If you buy an irrigation system and you've invested tens of thousands of dollars, but you don't bother to turn it on, it's probably not a wise decision. Furthermore, if you don't manage it and run it when you need to, as far as maybe you're putting on too much, too little, you can actually hurt yourself. So are you going to manage this correctly, and are you going to invest the time to do it right? And then finally, we're going to look at whether it comes out to be profitable. Please stop me anywhere along this, because we can make a sideline and talk about something else. So whether it fits your farm or not, if you're in this category here with a sandy loam or a loamy sand, and you've got shallow soils, which we typically do on Delaware, you're talking about somewhere in the neighborhood of holding I don't know, maybe an inch and 2/10, somewhere there, an inch and 2/10 to an inch and 8/10 in that available water holding capacity. If you're lucky and have some of these soils, you're holding double that. So the analogy I use is we've got a glass that we're holding the water that our crop is using in. If you're in Iowa and you have 10 plus feet of topsoil with high organic matter, you have a 5-gallon bucket. If you're in Sussex County, Delaware, you have a shot glass. So if you're going to stay hydrated in the summertime, you're going to have to fill that shot glass a lot, pretty frequently. Think about it that way. So the coarser the soil, the smaller the glass. The shallower the soil, the smaller the glass. Okay, different types of irrigation systems. So the first one's going to be a traveling gun. Management required is very high, because every time you get done with a pull, you've got to move this thing. It has some negative effects due to wind. It's going to require quite a bit of pressure, which makes its operating costs go up pretty big, because you need 80 to 120 pounds of pressure to make the water get the distance you need to. And anytime you double pressure, you are doubling your energy requirement. So if you go from 40 psi to 80 psi, you will use twice the fuel for the same flow. Okay, just think about it that way. I've got crop potential as being fair, because small seeded crops are not going to respond well to a gun shooting 300 feet and hit it with large droplets. It's going to hurt you. It's going to knock stuff back. Center pivots, moderate management required, because you still need to go out and determine when we're going to turn this on and manually turn the thing on. Yes, you can do it remotely with your cell phone now. But for the most part, you do need to lay eyes on that field and go take care of it. Make sure it doesn't have flat tires. Make sure somebody didn't leave the combine underneath the pivot before you turn it on. Those types of things are pretty important. Operating costs are fairly moderate. As a general rule with a center pivot, whether you're running diesel or electric, you're going to be in that $4 to $5 per acre inch of water applied. So for every inch you put on each acre, it's going to cost you between $4 and $5. There's a little bit of variance there depending on what kind of pump you have. You've got excellent crop potential, and lifespan depends completely on what your water quality is. I have seen scenarios where center pivots won't last but 7 or 8 years because the water was awful. I've also seen scenarios where they're 35 years. That's as good as it gets. As a general rule, about 20 years you need to be looking at, maybe we've got to replace this thing. At that point in time, it's starting to get used up. Subsurface drip, we're not going to go into a lot of detail on subsurface drip, but I'm going to gloss over it, mainly because it is an opportunity for fields that are oddly shaped, that don't fit a center pivot, that's got an arc to it, to irrigate those. Now, management is moderate in the later years, low in the early years. And that's because when you first put it in, everything works great, but as you get later on in the lifespan of this system, you really need to walk that field and find out where your leaks are. And if you don't find that leak, you will find it with a combine that fall. The other challenge you've got there is from a crop production standpoint, you're not going to water in a herbicide. You need to run it like in a double crop soybean behind wheat. Normally you would shut an irrigation system off while that wheat is maturing. Depending on your soil type, you may need to run that through that wheat maturing period to keep that soil wet enough so you can germinate those soybeans later. I have seen scenarios where I really had to wait for a rain because you can't get that water to push up in a sand to get to the surface. Now, if you're fortunate enough to have silty clay loam or a loamy soil, okay, it will go up. You are going to use in a sand, you're going to use more water with an SDI system than you would a center pivot, simply because you lose so much trying to push that water vertically, you're losing so much at the bottom end. Okay. Pumping wise, it's very efficient because you're not generating much pressure. It costs about half to pump the water in an SDI system that it does a center pivot. We don't know exactly how long these are going to last here, but there's places in this country that have had them out there in excess of 25 years and they're still working. It's more and more be a matter of how long can you go without messing the system up by either having a filter failure and filling it full of sand and or an algae issue or something, or an iron issue or something like that, and ruining it. With the SDI system, you don't have the option to go unplug the nozzle like you do a center pivot. Yield potential is great on it too. And then finally, this is a vegetable scenario where you're running tape on top of the ground. So that's a very specific case that I'm not going to get into. So pumping wise, you've got 3 options. You've got centrifugal. That's what you're typically going to use in a surface water scenario. They're fairly cheap. You got to prime them. You can run them with any power source, whether it's diesel, electric, whatever. But you're not going to lift water more than 20 feet. Just not physically possible. But you don't have to worry about it. If you shut a valve off and deadhead this pump, you're not going to destroy it. Some other pumps you might. A turbine pump looks like this. It's going to be down in the well. Around here, they're set probably 60 feet. Other parts of the country, they may be set down to 1,500 feet. You're going to have a shaft running all the way to the surface with a motor like this on top of it. A submersible and a turbine are near about the same pump. The difference is the motor is directly coupled to the pump and put down the well. Submersibles work great until you get to about 600 gallons a minute and more, and then they start to get pretty inefficient. And that's due to the fact that this motor here is a 40 horsepower motor here. In order for me to make a 40 horsepower motor that's small enough to fit down a well, it's got to be 6 to 8 foot tall. And from an engineering perspective, that's a very inefficient design as far as being able to turn that pump. The least efficient way you can pump water is going to be a submersible pump with a genset. You will burn the most fuel of any of the options, and here's why. Whenever you convert energy from one form to another, you lose a percentage. So in a genset submersible scenario, you're converting fuel energy to mechanical energy in the engine, that mechanical energy into electrical energy in the generator, the electrical energy into mechanical energy in the pump, then the mechanical energy into water energy to get your water for your system. So every time you go through each of those steps, you're losing a little more. With a scenario where you've got a direct coupled turbine where the engine's hooked via a mechanical connection, you drop about 3 of those potential losses. So there's plenty of gensets and submersibles out there, and they work fine. You're just going to be conscious you're going to burn a little more fuel. Okay, so pop quiz. How would you irrigate this farm, everything you see on the map? Anything stick out as being blatantly obvious, easy way to irrigate it?
Big circle.
Big circle. And it's a big circle because it was pushed out with a bulldozer to fit the field. Now there's somebody in here that might recognize this farm. Makes for a great example. So in this scenario, you can get a pretty cheap irrigation system in there. Now we're just talking about the cost of the steel above ground. We're not talking about pump, we're not talking about well. By the time you put that in, you're looking at about $578 an acre to put in a 188 acre system. That's pretty stinking cheap. That's about as cheap as it gets. And you don't run across those scenarios very often. You don't usually see 9, 10, 11 tower systems that are out there. Okay. So what becomes a little more challenging is if you were to move across the tax ditch and look at the field adjacent to it. So this is about a 48 acre field. If we were to irrigate this with center pivots, we need a 2 tower that ran in a full circle scenario and a wiper system that just covered this part of it. We would only cover 38 acres of the 48 here. And we'd have about triple the cost per acre as we did that big pivot before. So that's where this gets really tricky, is because field shape really drives the economics behind all this as to whether you can make it work. Then you got the other challenge of, all right, we've got about 10 acres of dry land that needs to be managed differently than what's under the pivot. How do we handle that? Well, the one other option would be to put in subsurface drip, where you're going to get the whole farm, but you've got the other associated challenges. You're not going to put vegetables over subsurface drip just because you have some harvesting challenges that you can't wait for it to dry out and not rut the field. If you rut the field up with subsurface drip, there's a good chance you're going to destroy it. So you need to really have a scenario where you can wait for it to dry. You know, you can get that subsurface drip at about the same price as we were for the 2 center pivots that were in there. However, you're going to cover the whole field instead of 3/4 of the field as far as being irrigated. And then finally, you can get the nightmare scenario of putting a traveling gun in there and having 6.5 pulls. You're not going to get any sleep. You're going to have a mediocre crop, and you're just going to be generally grouchy because it's a nightmare. Okay? So, how many acres are you irrigating with a gun? With one gun? Over what soil type? Okay, so you can get away with that because you're putting on, okay, so there's a scenario where it wouldn't be that bad. We're talking specifically crops, and I'm focused mainly on sand. With this, in the sandy soil like this, I need to irrigate that whole farm about every 3 days. That doesn't make it practical. If you're in a silty loam soil and you're doing hay and you can irrigate once every 2 weeks or once a week, then you can probably manage it. It all depends on your soil type. So from our standpoint, growing corn, that's not going to work. All right. Any other examples of times when you prefer to have a traveling gun? Because this is almost Delaware specific. When you get into better soils, it gets to be a little better of an option, a little more viable option. Okay. So when we look at cost per acre on this axis, ranging from 0 to 5,000, and then the size of the system ranging from 0 to 200, if we were to put in SDI, we're going to see a curve that looks about like that, where we start off at about $2,700 being our worst case scenario on the bottom end, because we're small field at like say 5 acres or so. I stopped that graph at 100 acres because we typically don't see any systems in SDI that are bigger than about 40 around here. In Texas, it's very common, but you don't see them around here. On the worst case scenario with SDI, that graph moves up to about 4,000, dropping down low below 2,500. This includes the pump and the well and the tape installation. So the difference between the worst case scenario and the best case scenario would be, a best case scenario would be a long, narrow field where you can get a 1,000-foot run of straight tape and have one plumbing connection. A worst case scenario would be maybe only 300-foot long runs, so you have a lot more underground plumbing to do versus the amount of tape that you have. So when we lay in a full circle center pivot at about 20 acres or so, it makes more sense to put a pivot in, provided it can go full circle. When you go to half circle, so it's a wiper system and you can't make a full circle, that line crosses somewhere in this 30 to 40 acre range. And that's why I say we rarely see SDI systems above 40 acres around here, because it's just easier to put in a wiper system. Okay. So, and then you've got, there's disadvantages and advantages to each, but it's by case basis, it's basically usually done by size. Okay, questions? Okay. This is going to go fast. So, we're going to talk about every number on this chart. No. This is a free Kansas State University Mobile Irrigation Lab cost calculator. There's also one for Nebraska, and this was actually written by a guy from Nebraska, but it came from K-State. Don't ask me how that happened. However, there's no need of me recreating this or you recreating this. Use the ones that come out from out west. These irrigation cost calculators work well. The basis behind them is solid. So if you're looking for this, look for Kansas State Mobile Irrigation Lab and then irrigation cost calculator. So in this, I'm going to go through some of the numbers just to get an idea of the factors that go into play. We need to know how many acres are irrigated, and we need to know pumping water level. How far down are you pulling the water from? That has a big effect on how much energy you're going to use, your operating costs. We also have to know what kind of pressure you're operating at and how much water you're going to put out per year. I generally use a 9 inches per year factor, because over a course of number of years, we usually range from about 6 to 12. 9 seems to be a pretty good number to use.
Okay.
Yes?
Would you have irrigation at all? Do you make assumptions on your...
You're going to have to guess.
On the pumping level?
Yes. You're going to have to guess. So I can tell you roughly what your numbers are depending on where you are. The best one to talk to is going to be a local well driller that's familiar with the area. They can tell you, here's where we find water, and here's probably where we're going to set your pump. And it may change a little bit, but those guys generally know the aquifers and that kind of stuff. So, we've got an ROI here of 5%, and you'll see in all this we're looking at a return on investment of being 5%, because if I'm going to invest $100,000 in an irrigation system, or take that $100,000 and put it in an investment, I need that irrigation system to at least make what I could do investing it and not having to work for it. So we got to factor that 5% return on, and then maybe your number needs to be a little bit different than that if you're a better investor. Then we got costs associated. We got the cost of the well, the cost of the pump, the cost of the gearhead if it's a turbine, a pump base, and then the pivot itself. So in this scenario on a 50-acre system, we're looking at an initial investment of $76,000 to get this thing in turnkey in a shallow well scenario. You got ownership costs over time and operating costs. The big numbers are right here. It costs about $214 per year to own the system and $44 a year to run it. That's counting labor, that's counting fuel, all of that. Okay. If we switch to a diesel system, the ownership costs stay the same, but the operating costs go up about 5 or 10% just because you're burning more fuel or more expensive fuel. So I encourage you to run this spreadsheet before you buy an irrigation system so you can get a real good handle on what your actual costs are. So I'm going to make some general system analysis, just kind of say here we're going to take a stock system. This is a system that I'm looking at about a 60-acre field, full circle center pivot, on a loamy sand soil. So making the assumption in loamy sand that you're probably not going to be planting high population corn. So in order to maximize the return on that irrigation system, you're going to need to bump your population up. So we're going to have an increased seed corn costs. We're going to have an increase in fertilizer because we're expecting a greater yield. We'll probably want to run fungicide because we're going to irrigate it intensively, and we're going to have to pay about $50 a year to pump the water. Okay? I'm going to also make the assumption that we're running a corn, soybean rotation. Some other stuff we look at later will be continuous corn, and there was a long discussion earlier about can you run continuous corn? Yeah, sure you can. You're just going to have to, as Cory says, it depends on whether it works for you. I think it's, so you're going to have to figure out for yourself as to whether that's something you can get away with or not. So on this corn bean rotation, by the time we get done with the ownership cost of the system and repairs, it's going to cost us about $277 a year to own the system over a 10-year return on that, or 10-year depreciation, and it's going to cost us $277 with all of our factors into play on a corn bean rotation. If we assume loamy sand will give us a potential yield increase when we irrigate it of, say, 125 bushels of corn and another 25 bushels of soybeans in that third year, and $4 corn, $8 beans, I understand they're not always going to be the case. We're going to see a return of about $400 for a $277 investment. So you're going to be in the good by $133 in that scenario, assuming all these estimates are right. Okay. If we go to a sandy loam, the only difference here is going to be our yield potential isn't quite as great because we're starting with a better soil in a dryland scenario. Maybe we're only going to go up another 100 bushels by irrigating it in corn. So in that scenario, we've got, what, a $66 benefit on that corn rotation over a 10-year period. Okay. Now, the big one that drives all these numbers is this irrigation ownership. That's the elephant in the room as far as costs, and I'm assuming a $1,500 per acre system. That seems to be kind of average. If you're in the $500 per acre 11-tower system, okay, this is easy. But if you're in that $2,500, $3,000, sometimes more scenario, that elephant is really going to take over the whole equation. Okay. And finally, if we look at a loam soil, where we've only got a potential yield increase of 75 bushels of corn and 20 bushels of soybeans, you're going to lose about $20 a year over a 10-year period by irrigating. Factor in all those costs of what it costs for labor to run it, maintenance, repairs, fuel, etc. How many people were expecting to see, hey, sometimes you're going to lose money by irrigating? Okay, good. All right. So this is a little bit hard to look at. Bear with me. This is a three-dimensional graph looking at yearly returns. So anything above this line, there's a plane here, is a positive return on investment. This is our potential yield increase in corn. This is a continuous corn scenario. So anywhere from 25 bushels more corn per year by irrigating up to 200. And this is our system size in acres. So from 6 acres up to about 200 acre system size. Anything in blue is a positive return on investment. Anything in red is not. So we've got this line here that shows where you're going to make money. So if we look at 50 bushel potential yield increase, there is literally no scenario where we make money with this system over a 10-year depreciation on the system with a 5% ROI and $4 corn. Okay. If we can get 75 bushel better, okay, as long as we're looking at a 72 acre system or so, or bigger, it pays. Okay. Questions on that? If you're into dark blue, I want to know why you didn't put it in 20 years ago. Okay. So if we change that to $3 corn, that graph gets pretty ugly. Okay, there's very few scenarios, unless you're looking at a pretty sizable yield potential increase and a pretty big system. Okay. If we look at $5 corn, it gets pretty good. Now, one could argue pretty quick that, you know, here's 25 bushels. No, you don't ever make it work with a 25 bushel yield increase. But at 50, as long as it's pretty big, and if you get it a 100 bushel yield increase, shucks, you can get down a 25 bushel or 25 acre system and it comes out. That's using 10 years of depreciation. Okay. I think 10 years is a pretty valid number because we've already established that you've got 20 years max. It can be 15, on average 15 to 25. If you're in that scenario where you need to replace it at 15 years, I don't want to use a 15-year depreciation because by the time you've depreciated this thing off, now you got to put it back up again. You've never really had a chance to make any money on it. So I want to figure on, hey, we're going to pay this thing off in 10 years. Yes, ma'am.
So I'm assuming that not many people get 200 bushel increase. What's a typical increase?
What kind of soil do you have?
Loamy sands and sandy loam. I mean, are you seeing 100?
So the best way I think to put it is it's year in and year out irrigated. I think it's reasonable that you could consistently run about a 250 bushel average corn yield under the system. I think that's There are people that are doing much better than that, and there are people that don't make that number very often. So if you're in a scenario where you're getting 100 bushels a year on average, well, then there's a 150 bushel potential yield increase. If you're in a scenario where 1 year out of 4 you're going to get a 0, then it starts to come out. So it just depends on what you're capable of. But you are not going to buy an irrigation system and miraculously turn into Randy Dowdy and David Hula. It's not going to happen. They were a long ways getting to that point, and they've got the skills and they've got the ground to support it. Now, 250 I think is reasonable. Agree with that?
Yeah.
Okay. I always confer this. Consult with the agronomist. Us engineers tend to have our own thoughts, which are sometimes warped. Okay, so if we change from a $5 corn scenario back to the $4 corn, 10-year depreciation that we started with, yeah, Ben.
Isn't it sometimes hard to figure some of that stuff out, because if you were dry land versus irrigated, you can make your marketing decisions as far as contracts.
Yes, correct. You can look at, you have a lot more flexibility from a marketing standpoint. You've got potentially a reduced insurance cost because hey, if you're all irrigated, maybe you only need cat coverage. I don't know, because that's going to be your major risk around here. But at the same time, you're going to have an additional insurance cost because you don't need to insure that machine. The wire can be stolen. They do turn over. You do have to look at that cost. You're going to have additional costs because you have to make more trips to the grain mill. If you just doubled your corn yield, you're going to have to make double the truck trips. That's a cost. You got to pay somebody to do that. There's a number of factors. So yes, you are correct. There's a whole bunch of stuff we're not even going to touch on as far as giving you flexibility. It also, putting that irrigation system in, gives you that consistent year-to-year cash flow. You're not getting 200 bushels 1 year and none the next. So that's a sanity factor, or kind of thing. It's hard to quantify.
I just brought that up because I don't farm that much ground, but I know the farm that we put the irrigation on, year in, year out, that's our most profitable ground, usually by far.
Sure.
It has a lot of the stuff that we're not necessarily talking about in this room. Like we just talked about with being able to make marketing decisions, being able to pull the trigger on a nice price instead of having to sit there and wait till harvest time.
Right. Yeah, forward contracting is really hard when you don't know if you're going to have a crop. Yeah. So your only alternative to that would be to bin it. And then that, so to that whole cost benefit, the reason I don't like to quantify that is you're actually looking at the opportunity cost of putting the irrigation system in and be able to forward contract versus putting bins in and not have to, taking that assumption out of the equation. Okay, so now we're back to the initial graph with a $4 corn and 10-year depreciation. Look what happens when I go to 15-year depreciation. So if you're comfortable with that, and the neighbors are consistently getting 20, 25 years out of the system, and you're going to be using the same water, maybe you can use 15 years. If you use 20, which I really think is a bad idea, it's a pretty good looking graph. Okay, so you see what I'm getting at early on as to how hard this is to explain, because there's just so many factors that I can't say what your farm is going to do versus yours. So we've got any questions on this overall economics before I change gears into a little bit sideline here? All right, I do it. They just want to go home, Cory. They're burnt. Okay, so especially being we've got some NRCS people here that like to think that the latest and greatest technology works everywhere. I want to kind of show you the latest and greatest technology on irrigation is going to be variable rate application. So I'm not talking about this scenario. This is speed control. Some people call this variable rate irrigation. While I would agree technically it is, but it's not in the traditional sense. I can speed that system up and down, going around the circle, and end up applying more or less water, but you get these nice little pie shapes of application, and the variability is never in a pie shape. So that may not be an ideal scenario. What I'm really talking about with VRI is this zone control where parts of the machine is coming on, some parts of it are going off to apply different irrigation rates. So there was a study out of Nebraska with Valley that looked at where this fits, and this particular farm had a wetted area raw variability of 26%. That's a complicated way of saying 26% of the farm was not being irrigated optimally with a straight system. Okay. If they go to speed control, That gets to 21%, we drop about 5% better job of irrigating. Okay, so 21% is not irrigated optimally. And then if they get into sector control, 7.4 of it is not irrigated optimally. That's one of the limitations of the system. We get down to 7.4. Okay, so when they looked at that system, they saw about a 12% reduction in water application in that particular field and about 15% reduction in nitrogen application because they're putting it where it needs to be. All right. So if we run the numbers on that, we've got to do some mapping to have them optimize the VRI for the field to come up with a plan. We've got to pay for that service to get it done. We've got to pay for a panel that's a more expensive panel than our stock one. Or if we go to zone control, we're looking at adding, on average, $20,000 to the cost of the machine. Now, the big cost here is not, to me, is less the cost of the hardware and more this maintenance cost. These things are a pain in the butt to keep working, okay? They plug up. I generally am, during test plots, we're working on that thing once a week, unplugging or fixing a half a dozen nozzles every week. I don't know anybody that has the time to deal with that. If you've ever dealt with a corner move system where the corner unfolds, if you've ever had one of those, about 90% of the time when you have a service call, it's for that stinking corner. A VRI is probably 4 or 5 times worse than a corner, in my opinion. Okay. So you've also got problems if you've got dirty water or rust or all that kind of stuff because there's very small orifices in those valves and they'll plug up and they will work. Okay, so if we look at that part, we need 900 to do the little pie shapes. We need a $900 per year increase for sector control over 3 acres. We've got, it comes out in the long run, we've got to grow 56 more bushels of corn over 3 acres to justify owning that. So by speeding that system up and down, can we really get 56 more bushels of corn out of it over 3 acres under that system? Maybe you can, maybe you can't. That's just figuring an average 50, 60 acre system. If we look at sector control, the individual nozzles going on and off, we got to have 88 bushels across 9 acres more by changing that onto it. And that's an unlikely scenario. Unless you're paying for water, these things generally don't come out to be a profitable venture. And that's why the only place you see VRI being used under a research scenario in some very high water restriction areas. Flint River between Georgia and Alabama. They're being paid for by conservation districts and whatnot because there's a whole battle between Alabama, Georgia, and Atlanta for the same water coming out of the river. So, unless you're in the extreme case, VRI probably isn't a good idea. So with that, that's most of what I'm going to talk about, unless you've got specific questions that we want to kind of discuss.
Didn't you pick on NRCS?
Yes, ma'am.
I have to ask, so are there states where NRCS is cost sharing on?
Yes, yes.
Where?
Nebraska, I think, maybe parts of Texas. They're looking at it as a conservation practice because there's parts of the field that are not farmed, so they're shutting the thing off. I would say you can see some really odd irrigation layouts when you get away from here, to me. Scenarios like one Cory and I was at, I would say he probably had a 100-acre field and 25 acres of that was a pond, and the irrigation system walked through the pond.
That happens a lot out west.
Well, this was in Georgia. And they said, well, we needed the VRI to shut the water off over top the pond. We just wouldn't have ever made the system go over the pond to start with, you know. So, there are some scenarios. Now, if you've got rock outcroppings, then okay, you don't really have a choice, and that's a valid use for that. So, sometimes people in Southwest have blow sand areas in the middle of that's never going to grow anything, so they'll just turn the water off. Yes, sir.
Another thing I didn't hear you talk much about is specifically relating to management of soil water in the system, using potentiometers, some blocks to measure that. Have you ever looked at the economic benefits that that has?
So now that's another 2-hour talk. So to make a concise answer, yes, we have looked at using a various number of management strategies, specifically soil moisture sensing. In our experience, farmers are not willing to invest the time to actually use them. The example of the case, we had 20 systems, soil moisture sensors, that we installed for 20 different farmers. They had 4 stations in their field, relayed all their data back via the web. They could look at it on their cell phone, iPad, whatever they wanted to, for free. We owned them, we installed them, and we made the maintenance and removed them. And maybe 25% used them, and when we pulled them out, nobody out of 60 farmers ever bought one. None. They said they were more than willing to let us put them back in for free. But yeah, so the reality of the situation is a lot of the soil moisture sensing technology just doesn't get adopted. And I think the function of that, if you were in an arid region where you're getting 12, 15 inches of rainfall a year, it proves itself to be more valuable. Here, where you can count on getting reset by rainfall, every couple weeks. So the sensor becomes less valuable in that scenario. The best tool you can buy for managing irrigation is a soil probe. Learn your soil, probe the ground, figure out what you've got, feel it, work with it. You'll learn a lot of other ancillary things beyond irrigation while you're doing that. Yeah, Ben.
You got a farm that's on a road with single phase of, what's the cheapest, most efficient way to get 3 phases collected?
Put a polyphase converter in. So,
Is that through the co-op?
yeah.
Electric co-op? They still have that program, even they split it?
I haven't heard that they've stopped it, but I'm not in regular communication to find out. And last I knew, they were still doing it. So what he's referring to is if you don't have single phase power, you want to get 3-phase power to your farm, and there's scenarios where you're going to have to pull 3-phase 4 miles to get to your farm. You can't afford to do that. It's generally about $20,000 to $30,000 per mile. So in that scenario, you can put in what's called a polyphase converter, which takes a single phase current, uses solid state electronics to convert it to 3-phase. It does the same thing as a rotophase. Rotophase works too, but if you can get the electric company to pay for the converter, that's way to go. A polyphase converter and a VFD are the same thing. They're the same thing. Yep. And the benefit you also get with that is you get a soft start feature. So the one thing to quickly mention, if you've got an electric pump and we turn that dude on today for 30 seconds, you're going to get a $200 to $300 demand charge. Boom. Right there. Even if you turn it on and turn it right back off. Now that only happens once per billing cycle. So we could turn it on 100 more times this month. And that charge isn't going to hit you. You're just going to pay for the electric. But when you turn that thing on the first time, you're going to pay that demand charge. So think about that. That can hit you pretty hard. If you're just running it one time, your cost per kilowatt hour is going to eat you up. The advantage of some of these polyphase converters and VFDs, or even just a soft start box, is it's going to knock that demand charge at about half. Because when you start an electric motor, I'm thinking of one on a 30 horsepower pump that we've got. The running amp draw is, I think, like 28 amps, but the start amp draw is like 60. Okay, that's what they're getting that demand charge is that peak draw. So if you can run a soft start box that spreads that starting time over, and you don't see that 60, it may only go to, from 28 to 35. So it backs off on that demand charge. Sometimes, a lot of times, the soft start box pays for themselves.
Co-ops requiring that now.
The co-ops requiring it now. Are they requiring it to be installed on old systems or just for any new installations? Okay, I did not know that.
For 30 horse and above.
For 30 and above, okay. Other questions? All right, go home. Thank you.